Okay. Um, just some quick acknowledgements. Joe Armstrong for the legacy that he's left us with, and our conferences team, Gurpreet, and your crew. Thanks. Eh? All right. So my talk is about some design patterns which we find in Rabbit, which I think are useful and can be reused in other Erlang applications and Elixir applications. All right. The title of the talk was Innovative, Unorthodox, blah, blah, blah. I removed the innovative because I'm not sure what you guys are going to think about this. So it's up to you to decide whether it's innovative or not. But anyway, a quick overview on Rabbit. So it's an Erlang implementation of AMQP, and recently it's including Elixir. So the CLI tools are all based on Elixir now. So it's now both Erlang and Elixir. And you've got a lot of client libraries in different languages. So literally, I can't think of one language which can interact with Rabbit. I know Brett Cameron even got COBOL working with Rabbit. And yeah, it's been around for a while. I think over 10 years now. And there's over 35,000 known installations of Rabbit. So in terms of being one of the most popular Erlang systems around, Rabbit is up there. So yeah, basically you've got your producers pushing messages to a broker or a cluster of brokers, and consumers fetching those messages. And yeah, basically just queues pushing, apps pushing messages on one side, and consumers getting that data. And then a bit on the internals. So what you have is you've got a publishing application, you've got a socket reader, right? And when you push a message, for example, this is when you're just publishing a message. The reader will obviously get that message, and there'll be mediation, basically converting the frame into an internal Erlang record, and then that is pushed to what is known as a channel, which is basically Erlang processes, which basically multiplex the TCP connection. And then there's a lookup in Amnesia to get the route for the destination of that message. And what you get from Amnesia is basically a list of queue PIDs, right? And then that message is then forwarded to all those queues, which can be distributed across different nodes in a cluster. And that goes through an internal API, which we'll touch on later. And then when the message gets to the queue process, it's either delivered, there's a first delivery attempt to the subscribed consuming application. And then if the consumer is not available, the message is pushed to the message storage. Right, so that's written to disk or it's kept in RAM, depending on your config. All right, so that's a bit on the internals. Right, so our discussion today, we're just going to go through just the following. So basically, if we just look at Rabbit from a top level view, you've got the application, then you've got external applications, which are called plugins, but it's just Erlang apps. So yeah, we're going to look at initialization, what can be useful for you guys when you're initializing your apps, which you can steal from Rabbit, supervision, and then some processes and behaviors that you can reuse. All right, so the first part is what is known as bootsteps, right? So Rabbit uses a concept called bootsteps for initialization, right? Basically what it does is you've got a set of procedures which are defined in different modules or different applications, and those are read on startup, right? And those are defined as module attributes, right? And then when those are read, you get the specification which is going to be executed. I'll show you how that works just now. Then you've also got some preconditions, so you can say, so this step depends on something else and requires another step to have initialized, right? And I think it's an alternative to OTP application start phases. So if you've used start phases just to initialize your apps, I think bootsteps are good. Well, I would say they provide more flexibility than what you get from OTP start phases. So how do they work? So this is very simplified, but yeah, just to explain how things work with bootstrap. So when the Rabbit node starts, right, the start function of the Rabbit module will be executed, and then there's a run bootstraps call that is executed, right? And then after that, all the bootstraps within the Rabbit application and any external dependencies are fetched. And that is basically done by getting all the module attributes with the bootstrap, right? And then once all those have been acquired, what Rabbit does, it builds a directed, how do you pronounce it? Acyclic graph, sorry about that. And then from that graph, it will basically create edges based on the dependencies, and then build a topological ordering of the graph, and then convert that to a list. So basically, you've got a list of all your bootstraps topologically ordered, and then from there, it will basically check which of the bootstraps are in loaded apps, and then it will execute all the module function and args which are defined in there, right? And basically, that's it. And that will be the startup procedure, right? So an example. So Rabbit has got the concept of exchanges. This is a fan-out exchange implementation, right? And as you can see, we've got the Rabbit bootstrap attribute. The name of the bootstrap is basically we just get the module name, you get the description, and then the module function and arguments are the spec, which is going to be executed on startup. And then, yeah, so this bootstrap requires the Rabbit registry bootstrap to have executed, and it enables the kernel-ready bootstrap. Right? So basically, what these two, the requires and enables, are what the directed graph uses to build the edges, and the vertex name is the bootstrap. Is the bootstrap name. And then you've got more of these, right? So the Rabbit module, which is basically what the app uses to start Rabbit, has got a whole bunch of bootstraps, which basically are used in initialization of Rabbit. So yeah, just a small example. So if you had a number of bootstraps across your applications, right? Those will be a graph will be created. And I think that's the cool thing about OTP, that we get all these utilities that are available, like the directed graph utils module. We can just get the topological sort of your graph, and then your steps will be executed like that. So, yeah, that's bootstraps initialization. And then on supervisors, I should face this side as well. All right. So just a brief on, so Rabbit has got a lot of supervisors in its implementation, and most of them are based on a supervisor 2 module, right? So just a brief on this. I'm not going to go deep into this because I'm sure you've played around with supervisors, but what supervisor 2 provides you with, it's got just additional features like the intrinsic restart type, right? So if basically if a child exits normally, the supervisor will also exit normally, right? And you've got delayed restart types, like so you can specify a delay as part of the restart type. So what will happen is if your supervisor crashes, well, if it, I know like the default operation is that it will stop if it exceeds max restarts and within the specified maximum time. But with the supervisor 2, the supervisor will continue running, right? And it will attempt to restart the child that failed after that delay. So you get a few, few features like this, which are provided with that. And then you can also get find child utilities and some extra stuff. You can look at the module, and then, but what is more interesting, what are known as mirrored supervisors, right? So mirrored supervisors are a bunch of processes, well, only 3 processes, which act as a global supervisor, right? And then the child specifications of the processes that are started are stored in amnesia. And then processes, basically it allows you to have processes that can only exist once within a cluster, right? So if you've got a cluster and you say, okay, I just need this process to exist once, if that node goes down, restart it on another node. That's what you get with the mirrored supervisor. Then it's usually those processes must have a low state footprint. So if you don't want to have like a process with a massive, which retains massive state to be based on the mirrored supervisor. And then, yeah, I mean, I've mentioned that. And then the global name registration is not supported in the mirrored supervisor because it's based on the PG2, right? So it already covers that. So how does it work? So when it starts, so there's an overall supervisor, right? Which first it will check, is the global name specified? If specified, it will fail. If not, it will continue and check. Oh yeah, and simple 141 restart strategies are not allowed, right? If that is specified as well, obviously it will fail. And then it will start the overall supervisor, which will start a delegate supervisor and a mirroring process, which is actually which does all the logic for all the mirroring across your cluster. And then if that is started, right, this basically gets the child process, the mirroring child process, which will be started, and then it will send an init command, right? And then this will mark the overall supervisor is started. And then the delegate supervisor is pretty straightforward. So the restart specification that you specify when you're starting a mirrored supervisor is used by the delegate supervisors that will be started under the hood. So if you look at that, that's basically what the delegate supervisor will use. And that's it for those two. And then the mirroring process. So it would have started with, it's just a GenServer, right? It's based on a GenServer 2, which I'm going to touch on later as well. So basically what it will do, it will start and it will order the child specifications that would have been specified in the start command, right? And then it will basically retain those in its state, right? So basically state has got child specs and then the ordered child specifications. And then when it started, it will receive that init message from the overall supervisor, right? Which would have sent to initialization. And then this will create the process group, right? And then it will it basically adds that overall supervisor process identifier into the process group. And yeah, then after that, basically just checks if the process group name already had any processes or child specs, right? And then it will clear everything in amnesia, right, as part of initialization. And then after that, all the mirroring PIDs across the group, right? Because imagine if a process group was created and a process group already existed, right? So the PG2 module doesn't fail, right? It will just mark it as okay. And if other overall PIDs were available, all the mirroring PIDs will be extracted and monitors. So this is quite critical to the functioning of the mirrored supervisor, in that all the mirroring PIDs need to monitor all the overall PIDs. And that's how restarting on another node will work. So if one overall PID terminates, that down message will be captured on another node. And that's how it will restart the child specs in amnesia. And then after that, it will monitor the delegate supervisor. It will check if the child spec already exists in amnesia. If it doesn't, it will create a new child spec. If it did, it will check if the current child spec's overall supervisor PID is the same as the current one, and mark that as alive. So if the child spec already existed with an overall supervisor PID, that will just be, well, it will be marked as already in amnesia and fail, right? But if it didn't, it will stop the child process, and that will be supervised by the delegate supervisor. right? So overall, what you would have your overall supervisor with the delegate supervisor monitoring, supervising the number of child processes that you have specified, and then the mirroring server will be handling all the logic for coordinating supervision of processes across your cluster. And then all the supervisor API calls, which I'm sure you're familiar with. So like starting a child, restarting a child. So all those will go through the mirroring server, which will then link that to the delegate supervisor and add it to the child specs. Then what else? Yeah, then if a down message was received, let's say one of the overall supervisors had terminated, the new overall supervisor PID, right, on another node would basically take over supervising the existing child processes, right? So they'll be restarted. So, yeah. So that's how mirrored supervisors work. Yeah. And an example in Rabbit is the federation plugin. So federation links can only exist once within a cluster, right? Sorry, federation exchange links. So there's a good example of where we see this in use. So if a node terminates, and basically these are just TCP links, which are used for replication across wide area networks. And if you notice, it uses a transaction call for all the amnesia operations which the mirrored supervisor would use. And then, yeah, basically that's it. But like I said, you need to be careful when you're using this. You don't want processes that do a lot of work being supervised by such a supervisor. So in all the versions of RabbitMQ, the management plugin used to use mirrored supervisor, right? And we had one event handler which was fetching all metrics across the cluster, right? And that was becoming too much load on that single supervisor, well, single child process which was handling all that. And then basically that nodes would eventually crash, right? So, but with this case, federation links are quite lightweight, so it works well. And then some processes and behaviors we find in Rabbit. So the GenServer 2 module, process implementation, it has an internal buffer which extends the default message queue of your process, right? So what happens is if messages are received by the process, they'll be drained into that buffer, and then they'll be forwarded to your callbacks of your callback functions in your own implementation. So apparently it optimizes your selective receives because your message queue length wouldn't grow as much as it would if you didn't have that extension internal buffer. And then you've got additional callbacks like prioritized calls and costs and info. So you can prioritize your calls and costs, yeah? And then you can do pre and post hibernation. Those will also execute your callback modules. You can do backoff, right? So for delayed hibernation and variable timeouts. So timeouts can have some incremental logic based on this backoff. And then you can switch your callbacks, right? So you can actually return a tuple with become callback name, and then it will switch to another callback and transfer the state which would have been passed to the other module. And then you've got additional debugging and formatting capabilities. Yeah. So that's GenServer 2. Then, more interesting again, within the processes and behaviors in Rabbit is flow control. Right? So if you've got processes that are handling a lot of load, a lot of messages, you can actually implement flow control amongst the two. Well, that's what Rabbit does. So there's a concept of credit flow within Rabbit. Basically, it's based on process dictionary, right? And it only uses a single control message on demand when necessary, right? So it's very lightweight. And the concept is basically you've got a sender which is granted credit by the receiver, right, to send it more messages, right? And then the sender will block if it runs out of credit. And if a process is a transceiver, so both receiving and sending, it can't grant more credit to a peer process if it's already if it's already blocked, right? And the config is basically you initialize it with initial credit and then credit after, right? So how does this work? So from the sender's perspective, right? So the process sending will basically execute a credit flow send and specify the target process which is desiring to send messages to, right? So it will check in its process dictionary, is the credit flow default credit defined, right? If it is, it will use that. If not, it will get it from your application environment variable, and then it will check how much credit do I have for that specific process which I want to send messages to. So the context of the word from here is the peer process, right? So I'm getting credit from another process. So it will check if credit is equal to 1, it will block, right? Because we want to go below that, or we can't send more messages beyond that. But if it's not, it will just decrement, and that'll be it. That's and mark the process as able to send more messages. So if it was blocked, right, it will emit some blocked events, and it will set your blocked timestamp. So you can. So this is just for monitoring purposes. And then it will also look up as well the credit blocked. So you get a list of processes which were blocked, right? So this new process which just marked the current process as blocked will be added to the list of credit blocked processes. So, and that's how you determine if a process is blocked or not. So you can actually query processes for credit flow state, and it'll tell you whether it's blocked or not. Yeah. And then on the receiver basically does the same on initialization, right? But it uses a credit too, right? So it will check, and it will check the more credit after which it's been issuing, right? If that had fallen below 1, or if it's equal to 1, it will issue out grant more credit message. So basically, to send out an Erlang message, which is bump credit, to the process which has run out of credit in its own process dictionary, right? And on reception of that process will basically be able to send more messages. And yeah, and then it will also do some additional metadata logic, which is just, so for example, you can add credit deferred info in your dictionary. And then an example, so you've got process 1 and process 2, which want to implement flow control. So if this process, so if you queried state for this process, it would say it's running, and it will issue messages, right? But if that process was receiving messages, more messages again from another process, and then maybe one of these messages takes a long time to be processed by this guy, because whenever a message is received, if you're implementing the flow control, you need to ACK that reception. So if you ACK that and you notice that the credit hadn't fallen below 1, it will continue receiving messages. But if that hits below 1, well, if it hits 1, that's when it issues that message to the peer process to bump its credit up, right? So if you do that, this process will just execute a handle bump message, which will just increase the credit, its credit, by the more credit after, which was specified in your config. And yeah, basically messages will continue being sent. And then if that process were to terminate, it will issue, obviously you get your down message, and then there's a peer down call, which the peer process would execute, which would just clear all the metadata that you had about that other peer process. So that's credit flow. And that is used, if you look at the Rabbit implementation, that is heavily used between the socket reader and the channel, and the queue process, and the queue process and the message store. So if the message store, for example, was overwhelmed and decided to block the queue process, this eventually would block the channel and this will block the socket reader, and eventually the publishing clients will be blocked, right? So you'd see your connections, the connection state will be in flow control and blocked. Yep. So that's where it's used. And then more stuff in Rabbit. There's something called delegates, all right? So delegates provide us with an optimized means of internode communication, right? So you get both synchronous and asynchronous operations that you can use for remote procedure calls, right? So if you want to use RPC or GenServer call across nodes, you can actually use delegates for that. So you get a pool of delegate processes. So yeah, you don't really get blocking, and you can basically increase that based on your config. You also get process monitoring, which delegates provide. So you can set up monitors through delegates, right, which would only be on local nodes, right? So if you want to monitor a process which is on another node, that request to be routed to another delegate process on a remote node, and the monitor will be set up locally, and if a down message was received by that delegate, it will be routed back to your calling process. So this results in low bandwidth usage on your links, basically. And just a quick overview on how delegates work. Basically, so you've got, I think the two main functions, yeah, is delegate invoke, which is a synchronous call, and delegate no result, which I'll show after this. So this will basically group your PIDs, your destination PIDs, into local PIDs and the remote PIDs. So basically, grouped here is actually a map of with the remote node as the key, and the PIDs which you want to forward the message to as the values. And then this will basically compute the delegate to use, and then it will use a GenServer 2 multicast call, right? And then this will basically do a safe invoke. So this is now on the remote node. Do a safe invoke, and then yeah, basically you get the result. But if that process was local, right, it will just execute it on the local node. So your remote calls and your local calls are segregated before execution. And then for the asynchronous operations, it's similar, right? But this does a GenServer 2 upcast. So basically on the remote node, it will check for the delegate process that you specified in the call, well, that was specified in the call, and then execute an asynchronous call on the local node, right? So you don't necessarily use up a lot of bandwidth on your network links. So this is used on that API, right? So that internal API logic in Rabbit, when the channel wants to forward a message to a queue, because queues can exist across different nodes, right? So basically, that's where you find delegates being used. And just an example as well. If you've got 3 nodes, right, and you want process 1 to forward a message to multiple processes across your cluster, right? So instead of sending messages to each process, if you're using delegates, it would forward that message, right, to a single delegate, and then that delegate will basically split your remote PIDs and forward a single message to a remote delegate with the command to execute against the local processes. So you only have one call across your cluster instead of so this would have been 4 calls across your cluster, and this will translate to a single call, and all the local operations will be executed locally. Okay, and then there's more stuff. So you've got things like decorators and Rabbit. So these facilitating operations and maintenance. So you get dynamic state updates, right? So you can have a look at that as well. So this is very useful because in Rabbit we can actually change policies and the way queues operate in runtime, right? And you've got the GM, which is basically a behavior for attaining consensus on a group of processes, right? Which is soon going to be replaced by the Raft stuff, which Carl here is working on. And then you've got PMON, which you can use for optimized process monitoring, and you can also query processes on whether they're monitored or not. So these are things that you can just grab and reuse in your applications. And then, yeah, one more thing, plugins. Just a quick overview. So I think the plugin architecture in Rabbit is, is very useful. If you're building an application which is going to be exposed to, users who are not really into Erlang, but just want to operate your application. So the concept of plugins is very useful because through plugins in Rabbit, we get multiple protocols supported, right? And it's funny because users don't really understand what's going on. They just say, oh, I enabled this plugin, right? But under the hood, it's an OTP application that's been started, right? So, yeah, I think that's something which, you can also take the same concept on in terms of the architecture in building highly extensible systems, right? And, yep, all this is open source. You can find all this in the repos. And, yeah, that's it. Questions? Yeah.
So with the changes in OTP 22, is there anything that's going to change in your architecture?
Well, with Rabbit, I think if looking at the core team as well, so any change in OTP is actively being tracked. And I think the latest release is compatible with OTP 22. Yeah. And I think the master branch is already using some of the stuff which Kenneth spoke about, right? The Raft stuff. I think it's already using the persistent, indirectly. Okay.
Yeah, I see there's a lot of really great extensions to the OTP stuff.
Mm-hmm.
Have you considered or have you tried upstreaming any of this to the main OTP library?
Yeah, I think we should. Well, I think you can talk to Carl about that, because you can talk to Carl. Yeah, they make the decisions on that. Yeah.
Hey, you've mentioned delegates.
Yeah.
Are they developed as a plugin as well?
No.
No, so you would have to go and...
Yeah, but it's just a module called delegate.
All right.
Yeah, just take that, reuse it, put your name on it. Okay.
So first of all, thank you for your talk. It was great. You mentioned remote procedure calls and remote monitoring.
Yeah.
So what if the communication links between nodes start failing, like real bad? Are they recovering when connection is reestablished, or you need to restart the processes?
Yeah, well, that now depends on how your application is going to handle that. So, I mean, there's more stuff in Rabbit for handling cases like that, like network partitions and how to recover from that. So yeah, I think you'd have to add some logic on top of that. But in terms of the baseline concept, I think, delegates would assist you in that.
If you hear the keynote speech, there was a point about minimizing the interaction points. So do you think there's a connection between this pattern of delegates and reducing the...
Yeah, so I think with the delegates, because it's mostly, it's going to help, because some of the messages which are forwarded to the queue, right, in the case of Rabbit, they'll be carrying the actual message payload, right? So the whole, the new stuff which was spoken about, where large messages are going to be partitioned into smaller chunks, that's definitely going to be useful here. Yeah, so, yeah.
Any more questions?
But delegates use a queue as well, right?
No.
Just before they forward the messages?
No.
How is that implemented then?
So like I said, it's when you execute invoke, right? So what it will do, it will just compute. It's just a process. It's GenServer process, right? So it uses its own message queue, right? Yeah, and then that will forward that to a remote process.
Is there batching in messages sent to delegates?
Is the batching?
Is there a batch, or is one-to-one message mapping? Like if one node needs to send 4 messages to a remote node,
Yeah.
would that be batched by the delegate sent?
Yeah. So what delegates do as well, they'll maintain your order. So it's all abstracted, right? So it's as if you are still interacting with the process as in peer-to-peer communication. But yeah, delegates will abstract all that and still maintain your order. Yeah.
Yeah, I think that's about it then. Give Ayanda a hand and please leave feedback in the Wahoo app.